Hello and welcome to Hardware to Save a Planet. As we roll into the summer, I wanted to do another compilation episode with some of our best moments from the year so far. The theme I wanted to focus on here is all the ways different climate hardware companies are finding to scale their product or the market they exist in. In order to make the impact promised by the science behind these companies, they're all very aware of how much they need to scale beyond early prototypes, and they're all super focused on figuring out how to make that happen. It's fun to see the diversity of solutions we've covered so far this year, from making the ocean measurable, to electrifying semi-trucks, to reimagining how we make cement, to directly cooling the planet with balloons. But all of these guests share a really pragmatic focus on solving today's problems for real people and real businesses, as that's what will fuel the growth they need to have a lasting impact. First up is Allan Adams from Aquatic Labs. Allan pivoted from teaching string theory at MIT to building sensors for ocean carbon removal. I think about this space a lot because the consensus is we need carbon removal, but it has to scale so dramatically from where we are today. One of the things holding back that scale today for nature-based solutions is measurement, reporting, and verification of the removals. Here, Allan is talking about the importance of that.
I sort of think about this as, if you're running a gold mine and someone comes to you and says, I'd like to buy $1 billion of gold. And you say, well, that's great. Here's a big pile of gold. And they look at you funny and say, but it's invisible. And you're like, well, yeah, of course it's invisible, but trust me. I mean, that's the character of the problem that we're facing with carbon sequestration in the ocean. For the most part, these things are invisible at any sort of scale. And so finding ways to measure them is really crucial to the functioning of a carbon market for ocean carbon. And that's that's what we're trying to do.
And the cost of measuring those, and you said this too, but I think it's a really important point because the scalability of this market, of the carbon removal market, depends a lot on how much it's going to cost per ton to remove CO2 from the atmosphere. And that cost of MRV, measuring, reporting, and verifying that you've actually done that, the cost of that measurement is part of that cost. So if you're trying to get down to $100 a ton or $50 a ton or whatever it is, you've got to include that cost of every ton removed, the cost of measurement of every ton removed. So reducing that cost is super important.
Absolutely. And doing so in a way that's trustworthy, because at the end of the day, these are numbers that are going to be reported on the balance sheets of Airbus, Hitachi, Mitsubishi, and they're not going to put anything on those balance sheets that are not auditable with exactly the same rigor as anything else on their balance sheet.
Scott from Focused Energy is tackling what is arguably the ultimate energy solution, nuclear fusion. Scott's approach to de-risking the path to scale has been to build on the breakthrough at Lawrence Livermore National Lab that achieved ignition in 2022. Scott explains how this has allowed them to turn the problem into an engineering challenge as opposed to a science project, which could make their path to commercialization more predictable. So maybe this is kind of a fuzzy question, but like on the surface, when we talk about, virtually limitless, clean, safe energy, very inexpensive, this feels like it would solve all of our problems, kind of, right? Like this just feels like a hack to like it solves climate change, it solves like inequality, it's like, how do you think about? Is that the right way to think about this? Like, is this that big of a deal?
I think I always struggle with how to talk about that because I feel that it is so big that it almost loses meaning. Fusion is the end game for energy, which means fusion is the way that the universe creates energy. So at some point in technological progress, kind of meeting how energy is created in the universe itself is kind of the end game for technological progress. We will hit that goal. And frankly, we have hit that goal and we hit it 2 years ago. It's tremendously exciting. And so the commercialization of that technology is now, to my view, an inevitability. The energy potential of the fuel means that it will be an economic reality, that fusion will be the most inexpensive fuel source available at some point. The question is really when. And really, from my standpoint, I think that this is a requirement to the continued progress of civilization.
Luke from Make Sunsets takes a refreshingly different approach than many others in a couple of ways. One is that he's addressing warming more directly by reflecting sunlight back into space as opposed to reducing or removing emissions. And the other is that he picked a solution he's been able to start operating with very little R&D or investment.
The argument that gave me pause, like where I stopped what I was doing and thought deeply about it for several weeks, is perverse incentive. That if humanity has a tool to not need to cut back on our use of fossil fuels, we tend to be as lazy as we can get away with. We'll use that tool.
The moral hazard.
Exactly. And then I got out of my mental ivory tower and looked at the numbers a little bit and realized that fossil fuel use, greenhouse gas emissions go up year after year. We're not only not making any material progress zooming out to atmospheric levels of CO2. We're not only making little to no progress, we're proactively making the problem worse year over year. So the real politic of this is that, we need this, and most academics in the field, a lot of policy people consider it inevitable. They'll then bicker with me about like the politics of it and, is this making it harder for legit researchers to do it, blah, blah, blah. At the end of the day, no one else was doing it. So like you can't, and I like on these thorny political, philosophical things, occasionally we need to zoom out and try to quantify things. And, me not doing this when no one else was doing it, like it's not like a negative amount of this can possibly occur. It can't be any worse. It can't be any less occurring than there was before I started. Any particle you put up is going to have some warming or cooling impact, technically. Sulfur dioxide is, I think, the most reflective of the things that we've changed recently. There's also a large amount of it in aviation fuel. For example, a 747 flight from San Francisco to New York emits far more sulfur dioxide than all of the balloons that we've launched so far. So it's this comical thing where, like, I get it, our approach is different, but any quantification of the risk from what we're doing and the quantity that we're deploying, and also the altitude at which we're deploying it, compared to the ship plumes, we're something like 22x more cooling per gram that we deploy. That's why we'd have such a strong temperature, because we have longer residence time by getting to the stratosphere.
Curtis from Hydrostor represents something we've seen with a few other guests, companies that started over a decade ago when the market barely existed, but stuck with it through that long development cycle. Their compressed air energy storage system is now commercially contracted and building real projects. I really enjoyed hearing how Curtis evolved from using underwater balloons to using underground caverns, pivoting the approach to find one that is more scalable.
So now you have a pressurized air, 2,000 feet underground, and a thermal mass of 200 degrees C water kept in liquid form under pressure. And then when the grid needs power, the valve simply opens, gravity pulls the water down from the reservoir, pushes the air up, it goes back through the shell and tube heat exchangers, reheating the air close to 200 degrees C, and then it drives a turbine, which is just a steam turbine, and the air goes back to the atmosphere, and the grid gets power on demand. Well, the only moving parts really are the compressor and the turbine. Then you have a shell and tube heat exchanger, hot and cold tank, and a hole in rock, 2,000 feet underground. And you got a really long life, robust system for energy storage.
And can you say a little bit more about that? Like in what scenarios are longer duration solutions important than relative to shorter duration storage?
Once you start getting to reliability services, stuff where you need reserve capacity, but you're not always trading it, it's more sitting there as backup plants. That's really where you start getting more into a solution like ours, where you're doing arbitrage and you're sitting on reserve capacity, providing reliability services. Then you get into other solutions, which are just pure backup power. They're only used once a month or something. That's not really a good fit for us. There's other technologies there as well. We're kind of that intraday workhorse that you're charging and discharging every day, leveling the peaks and valleys, and keeping a little bit in reserve in case a coal plant goes down or a gas plant goes down. So 500 megawatts, 8 hours, that would be about a quarter of Toronto, the city of Toronto, 5-6 million people. That's just over a 2 gigawatt load from the city of Toronto. So we would do a quarter of the whole city, and we could sustain that for 8 hours before we have to charge up again. So it is impactful. It is meaningful on a city and a regional basis.
Cole's story with Pila Energy really resonates with me because it's about removing barriers to market adoption. He saw that whole home battery backup systems were not being installed as quickly as we need due to the significant upfront investment required. His solution is to allow people to start small with battery backup for the appliances that matter most to you. It's that on-ramp approach that could unlock adoption at a completely different scale.
Saw the opportunity to kind of do it different with Pila. Crude analogy, but let's imagine that we deleted all of the plug-in hybrid options for vehicles from the road. We delete all the regular hybrids. We remove level 1 EV chargers, the plug-in style. And we suddenly tell people, your only option if you want a better driving experience is to go full electric, and you have to have a fixed level 2, 240 volt, $5,000 EV charger. What would that do to adoption of the technology? Like, you've just yanked out the on-ramps for folks. That's the EV analogy. But today, that's the reality in home batteries, right? It's in smart home backup batteries, as there's really only the level 10 option. And most folks are starting at 0. So we have to ask ourselves, like, how do we create these on-ramps? How do we meet people where they're at? And, this concept of scalable, distributed batteries placed where power is most important to you, I see as really the perfect solution to that. And honestly, the obvious solution to that. By the napkin math, if you could snap your fingers and imagine a world where every home had a battery like Pila, 1.5 kilowatt hours, kind of in one location that mattered a lot to them, whether it was their fridge, sump pump, home office, terrarium, protecting their heat lamp on their lizard, which is one I've heard, right? If we had one of these batteries in every home, we would hit almost 10x the total grid connected battery capacity today. In other words, the sum of all power walls in homes, the sum of all container sized grid batteries next to solar fields. So there's a lot of power in distributed scale.
Greg's journey from robotics to consumer electronics to cement production shows how climate tech is attracting talent from across the technology landscape. Sublime is making a cleaner cement, but they know that's not enough. Their product also has to be better than the status quo to get the kind of adoption needed.
Cement is basically the glue that holds concrete together. So if you take cement, you mix it with gravel, sand, water, and some chemicals, that makes concrete. Cement is the binder, and concrete is what gets poured at the job site, what you see dumping out of the truck. So that's the main difference, is cement is the glue. It's actually only about 10% of the volume of the concrete. The rest is the gravel and sand and water, but it is over 90% of the carbon footprint of concrete is from the cement. And so the reason that process is so carbon intensive there's kind of two main drivers. Number one, since the kiln has to be fired at such a high temperature, I mentioned like 1450, 1500 C, the only way you can achieve those temperatures at industrial scale today is typically by burning coal or natural gas. And so that is roughly half of the emissions. Then the other half is limestone, it's calcium carbonate, and it's roughly half its weight is CO2 that's trapped in the rock. And so when you thermally decompose that limestone inside the kiln, all of that CO2 is released to the atmosphere. We call it next-gen cement. So it's low carbon, but it's also just how cement will be produced in the future.
Jason's work at Range Energy is another example of how companies are finding ways to scale quickly by leveraging rather than replacing existing assets. Instead of waiting for the entire trucking fleet to turn over to electric, Range is making the existing fleet cleaner today.
What our system does is it takes the perceived weight of that 60,000 pounds and turns it to 0. So all of a sudden, the tractor doesn't have to pull quite as hard, uses less fuel. We're not the prime mover, and that means that we don't have to always, the battery pack can run out, and that's totally fine. We actually want people to use the battery pack, because a battery pack that you don't use all the way that's extra money and that's extra weight that you're carrying around. As long as you have fuel in your tow vehicle and your tractor, whether that is battery fuel or diesel fuel or hydrogen or natural gas or whatever else, you're good to go, right? You're never stuck on the side of the road. But I think that also it sort of means that our technology is not just something that works today and reduces diesel costs and diesel emissions today. It's actually something that we're actually seeing early proof points that this really allows fleets that have maybe investments in EV tractors to actually utilize them on longer routes. We work with a fleet that usually ran their EV tractors on 60 to 70 mile routes. Like these are like internal transfer routes because they could not afford to, send have you ever seen a tow truck for a Class 8 tractor? It's like a really big thing. And, I don't know exactly how much it costs, but it's not cheap, right? And so that's the last thing you want to happen. You don't want to run out of juice and have to have a truck tow your truck. And so, after running a pilot with us, they're like, hey, actually, we can do a 200 mile route with this. We can do a 220 mile route with this. We can actually go up to 280 miles. And now we're running real routes, real customer delivery routes that we use our normal diesel tractors on that we probably never would have dared to run on electric. And now they can.
Nehali from Antora describes how they're tackling some low-hanging fruit in the energy industry to fuel their adoption. One point she shared with me that stood out is that the amount of wind energy alone that is curtailed in the U.S. Midwest is enough to power 10 million homes. That's just wasted energy that their solution gives us the ability to capture and use.
Once that core gets heated up, carbon starts glowing white hot. So it becomes like our sun inside that thermal battery. Then we have insulation around it so that that heat does not escape out. Then we have a mechanism which is like a door. We open that door to shine that light. I will not stop talking about this. It just makes me, it's hard to fathom how even now, like if I talk about US Midwest, about 10% of the wind that is generated is curtailed, which is about 10 terawatt hours of electricity, which is equivalent to usage of a million homes in the US. So that amount of energy is just getting wasted, and we don't have many technologies that can make use of that. So that's why we started thinking about.
Randol from Remedy Scientific takes a problem I hadn't fully appreciated before our conversation: contaminated land. There are 500,000 contaminated sites in the US alone, and actually the real number is probably much higher. Current cleanup approaches are too slow and expensive to scale quickly because each site is treated like an independent project. Randol is using robotics and AI to productize the cleanup process, so once his equipment is produced, it can be quickly deployed to any new decontamination site.
PFAS are called forever chemicals because they're really difficult to break down. And in fact, one of the primary uses of PFAS and why they're out in the environment in vast quantities is because they were used as firefighting foam. So they were a principal compound in this foam that was used to put out jet fuel fires. And that means that they're really, really difficult to break down. And so even incineration methods require 1,000 degrees Celsius. Desorption requires 400 degrees Celsius, very, very high temperatures to deal with this stuff. And ours is similar. We're actually doing it with, believe it or not, mechanical energy. So we're energetically grinding dirt, basically pulverizing it into smithereens. And that actually encourages the chemistry that breaks down PFAS. So instead of separating out PFAS from dirt or removing it, we're breaking it down while it's sitting there in the soil. For DoD, for PFAS, absolutely. That is a capped addressable market, and we want to go run the table on that market in like 5 years. Like we just should go clean up all of those sites, and that's very doable. The technology now exists to go do that. And I think that also means that we should be putting a lot more money toward cleanup and a lot less money toward investigation. The federal government is going to spend 4 times as much on investigation as they are on cleanup for PFAS this year. And we just need to start cleaning up these sites. We know where they are. We now have the technology to clean it up. We just need to get to work.
Ross from Transera is tackling one of those problems that feels invisible until you really think about it. Cooling buildings accounts for 10% of global electricity demand, and that's going to triple by 2050. Their approach uses new materials called metal organic frameworks to make air conditioning 40% more efficient while working in hot, humid climates where it's needed most. They're enabling scale by keeping the solution super simple and relying as much as possible on commodity equipment.
The same electrical hookups and all of the ancillary equipment kind of surrounding it is identical to what's out there today. And I think that's a real benefit that we have that can allow us or enable us to work with manufacturers to achieve scale quickly.
Yeah, it sounds like you've sort of architected to optimize for easy adoption, reliability, low cost, like
simplicity really drives a lot of those things. Was that, I know sometimes getting to the simple solution is actually a really challenging, complex road. Was that the case here? Was the idea from the beginning fundamentally simple?
No, that was 100% the case for us. We went through many iterations of trying to use the MOF in the system, and some of them were really complicated, and maybe they had, really high potential energy savings. I think the lesson for us and for me over time is that 80% their solution that is very simple will always beat the 100% solution that is very complex. And so achieving the simplicity and the readiness for industry adoption is really key for us.
Finally, Johanna from Azola Ventures is tackling the problem at a meta level. Traditional VC timelines and risk profiles don't align well with hardware development cycles or the capital intensity of many climate tech solutions. Azola deploys catalytic capital, which is a different approach that can take bigger risks earlier with a longer time horizon.
What is it that, and maybe particularly about these kind of physical innovations for addressing climate change, what is it about the traditional venture model that isn't serving their needs? Or where is the gap?
It's a few things stacked on top of each other. And I would probably first go to just the combination of timelines and capital outlays. So it's expensive. As you know, you run this podcast, it's expensive to pay for hardware, right? It's just the capital outlays are going to be much more significant. So any investor looking kind of down the pipe of how many rounds of capital at what scale this company is probably going to need before they reach scale and therefore get, some kind of exit, that's going to decrease the attractiveness in general of that investment. And then add to that in coordination with the capital outlays is the time duration. And traditionally, many venture funds are kind of 7 to 10 year durations. And so that means they're looking for returns on that timeline. And it's very hard to, commercialize. It's very unusual to commercialize a fundamental science and innovation that is encapsulated in a hardware technology and fully commercially scale it to its potential value in that time. The dollars that we invest think of them as they're like the grant dollars that a foundation would distribute out to an NGO or to, a policy kind of support organization. They are the type of dollar that would come from, a high net worth individual's donor advised fund that would be given to, any good cause. It is that type of tax exempt charitable capital that if you aggregate it, and this is what we've done, if you aggregate that, we are actually required by law, by the IRS, to invest that under two conditions. One is that there needs to be extraordinary impact potential. And two is that other investors in the market would not make the investment at that time. So there's almost like we almost do like an anti-investment evaluation, right? This has to be interesting, but not yet ready for other investors or not sufficiently supported by other investors. There can be nuance to it, but the point is the type of capital that we've aggregated it's a different color of money, we call it. And that color of money has different requirements. And that is the answer to your question, is how do we avoid just falling into the same old traps? It's required by the type of capital that we're deploying.
Thanks for listening in. Hopefully that gave a good view into the diversity of approaches teams are finding to navigate that tricky path from early prototypes to adoption at scale. If you want to hear more of these conversations, check out the full episodes. In the meantime, we'll keep finding new stories to share. Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.